Okay, so
Yay.
thank you very much. We're so close to being done with this, and this is perfect because we'll be finishing just before break. So we started by kind of looking at a little artwork by M.C. Escher, this mathematical art. Pretty incredible stuff. Um, then we did the lab with Newton's cradle, and we're actually going to do some referring back to Newton's cradle today. So remember how we picked up this one ball, lifted it up, let go of it so that it came swinging down and hit the other balls, and then it stopped. And then its momentum was transferred through these balls, and then this one had nothing holding it back. So it took that momentum and swung up into the air before gravity pulled it back down again, huh? So we're going to analyze the collision between this first ball and these other balls, both before and after the collision. So we came up with some questions to analyze. We defined the boundary of the system. We designed experiments, gathered data, presented that data in a visual format, analyzed our results, and came to some conclusions. Then we started doing some other things. Now this page you needed to do by yourself. So if you haven't done this, this is due today, where you read this and you highlight the important parts and you write some notes in the side over here. Similarly, you are supposed to have this finished already, where you fill in the word bank, fill in the blanks using the word bank as you go through. All right? So that was to be done on your own, including these two problems at the bottom. Now, these problems should not be very hard because all we have to do to calculate momentum is multiply. Here it is, P, that's momentum. P equals mv, mass times velocity. So remember that, we're going to use that today on the last couple pages of this project too. Then we started drawing vectors showing the momentum, the boundary of the system. We used different size shapes to represent different masses and different length arrows to represent different amounts of momentum. So this we all did together, and there's another video that goes over this page. And then I asked you to do this on your own. It was just practice of the previous momentum diagrams, showing people of different masses moving at different speeds. You calculate their momentum and draw a diagram. Make sure that you included the boundary of the system for each of these two, right? So you might want to double check that. And that led us to this page, which we did together last time. We looked at these collisions just between two objects, where in this case it was what? A ball colliding with another ball. And we calculated their momentum before the collision, and we calculated their momentum after the collision. One tricky thing we also did was find their velocity after the collision. And that takes us to this page. So this is where we're going to pick it up. So we're going to look at how we can use vector diagrams and make calculations of momentum to demonstrate what's happening in Newton's cradle. So in Newton's cradle, the balls moved in the same direction, in this case to the right. One ball stopped, and the second ball began to move. Well, actually, the fifth ball began to move, huh? Let's see what conservation of momentum has to share. So what do they want us to do? They first of all want us to calculate the momentum before the conclusion. Excuse me, let me say that again. They want us to calculate the momentum before the collision. They want us to draw the vector diagram before the collision. and outline the boundary of the system before the collision. So all of this on this top half of the page is about what's happening before this first ball hit the other ones that were just hanging there, motionless. That's 4A. Now notice in 4B, we're going to repeat that whole procedure, except it's going to be after the collision, right? So we're going to do a before and after, calculating momentum. Let's start with before. This is what I'd like you to do. I'd like you to do this yourself right now, and this yourself right now, and this yourself right now. Let me give you a couple of hints. First of all, I'm not sure why they did not say, as they probably should have, M3 equals mass 4 equals mass 5 equals mass 2. All of these had the same mass, right? All the balls had the same mass here. So it should actually say M2 equals M3 equals M4 equals M5 equals, and they're telling you that in this case, the balls were 5 kilograms each. Okay? So keep that in mind. All these 4 balls that weren't moving, and this one too, also had a mass of 5 kilograms. But we had to separate ball 1 because it was moving before the collision, right? We dropped this one, it swung down there, entered the system at a speed of 2 meters per second, right? Then it collided with these balls. Now these balls before the collision had a velocity of 0 meters per second. So what I want you guys to do right now is find the momentum here, and I'm going to be calling on people to give me these answers. Find the momentum of ball 1 before the collision, and find the momentums of all 5 of these before the collision. Since they all have the same mass, and since they all have the same velocity, they will all have the same momentum. Finally, we're going to find the total momentum of the system. P total before. P is momentum, the total momentum before the collision. And the way you find the total momentum is you just add up the momentums of each object in the system. So take a minute and do that right now. And then I'm going to start calling on you guys, all right? Please give me a thumbs up if you can hear me. Thanks, Andres. Oh, Alejandro, you got here. I'm so happy you joined us. Wait. Thanks, Kitsali. Okay. Cool. All right, so here we go. I'm going to start with Mr. Romero Crespo. I'm going to ask you to tell me what the momentum should be for ball 1. And if your microphone is not working, you can type it into the comments. What do you got, Alex?
Are we doing just the same thing we did with the last one, where we just multiply it?
Yeah, whenever you find momentum, it's just multiply.
Would it just be 10?
It's just 10.
Yeah,
simple.
10.
5 times 2 gives 10.
Okay.
Yeah, good job. I'm going to change that to red so it shows up a little more. All right. Next, for balls 2, 3, 4, and 5, they all have the same momentum, so you only have to do the math once. What did you get, Kitsali?
0.
Yeah, they have no momentum because they're not moving. Remember, this is before the ball swings down. Remember, this is Newton's cradle. So before this ball swings down and hit them, these ones aren't moving. If there's no movement, there's no velocity, and that means there's no momentum, right? Pretty simple math, yeah? Next is Gus. What do we get for the total momentum before the collision?
10.
Yeah, you just go 10. That was P1, huh? 10 plus 0 plus 0 plus 0 plus 0 makes 10. Simple enough, right? Okay, so the next thing I'm going to do is draw the vector diagram. And they've shown us how to do it the first time. So I'm going to grab a circle. I'm going to try to match the size of the circle that they did right there as well as I can. And since all of these 5 balls have the same mass, I want to use the same size circle every time. So I'm going to copy paste, and I can either go up to the comments. Sometimes I have to click on it a couple times to make this happen. There we go. Copy, and then I can go edit, paste, or I can do a shortcut on my keyboard. I hold the control button, hit C, and then control V, and I should paste it, right? So I'm just going to do that 4 more times, and then I'll drag these down to where they need to be. Hopefully I line these up in a nice straight line. It's not necessarily easy to do, so it doesn't have to be perfect, but the better you can do it, the better it will be, the more realistic it'll be. I actually did a better job today than I did last time. So there's my 5 masses. They're all the same mass. These ones are just hanging motionless. They have no momentum, so they do not need an arrow. They don't need a vector because they have no momentum. But mass 1 swinging in here at 2 meters per second does need an arrow to show its momentum. So I'm going to draw that arrow. I'm going to try to match the size that they drew. Looks like I made it a little too long, so I'm going to shorten it up a bit. And then the next thing I want to do is put some labels in here. So I'm going to label this momentum. I'm just going to label the total momentum. In fact, I'm just going to do it over here. I'm going to say total P equals 10 kg m per s, kilogram meters per second. Total momentum for the entire system, 10 kilogram meters per second. And then the last thing I need to do is draw the boundary of the system. Which they've shown for us is like this. So they're giving the ball a chance to swing in here. We're going to ignore it at first when I lift it. We're not analyzing that part of its motion. Only when it enters this region do we count it as part of our study. And then we're leaving some room for this ball to swing out. So we put a boundary on the system, a limit to our study. And I think we have finished the first half of this page. Now remember that after this collision, what's going to happen is that this ball is going to end up right here, huh? And this ball is going to swing out, right? It's going to swing out in a moment. And remember, this ball is going to come flying in here and slam into that one, huh? Once it hits this one, the momentum gets transferred through each ball, but they're kind of blocked from moving anywhere, aren't they? If these balls weren't here, this one would just swing back and forth, right? But this one stopped it. And so all its momentum was transferred to this ball. But this one was stopped by that ball, so its momentum was transferred to it. But this one was also stopped by the next ball, so its momentum was transferred over. But the last one was also blocked, second to the last one, also blocked by the last ball. So it transferred the momentum to the last ball, and that means this ball was able to swing out. Okay? And this is where we have to start thinking a little bit. It's not going to be just mass times velocity anymore, because what they want to know now is what is the velocity of the last ball after the collision? What does that velocity have to be after the collision? Let's think about that. Oh, here's a hint. Momentum is conserved. What is the velocity of M5, mass 5, or ball 5? What does the velocity have to be after the collision to maintain conservation of momentum? Then we're going to draw the vector diagram, we're going to do some calculations, etc. Now, I want you to pay really good attention to how we do this and the order that I do things, because when I turn you loose to work on page 16 by yourself, you're going to have to follow this same process on the second half of page 16. Okay? So the before the collision is pretty straightforward. You have a mass, you have a velocity, you multiply, you have another mass, its velocity is 0, so you get 0, and then you add them together. But here we have to work backwards to find the velocity. The velocity is not given to us. That's the big question mark right here. What is this velocity? That's what we're trying to get to. We're trying to find this velocity. This is actually the last thing we're going to do. We're going to do this first. This is easy. Then we're going to think a little bit about conserving momentum. And that is going to help us do this. From there, we get to go up to here. We kind of work backwards. Basically, we do this first. We do this second. We do this last. Not the same order as we did the before the collision. Are you with me on that? Okay, so this is what I would like you to do. First of all, there is another mistake over here. They should not have included P2, 3, and 4 right there. So scratch those out. Ball 5 is only by itself over here. 2, 3, and 4, we found their momentum already over here. So that was a mistake to write those again. Okay, so let me see. I want you to think about this. Remember, this is after the collision. Ball 1 swang down here and it hit ball 2. Now we're going to study it after it collides. What did ball 1 do then? How fast was it moving after it hit ball 2? How fast was ball 2, 3, and 4 moving? They were actually all had the same velocity. But ball 5 was different because it swang upwards and outward. All right, so let me see whose turn it is. I want you to tell me the velocity of these guys. That would be David. What is the velocity of balls 1, 2, 3, 4 after they collide? After ball 1 hits number 2, how fast are they moving? And David, if your microphone isn't working, please type in an answer.
0.
Yeah, perfect. Yeah, it just takes a little bit of thought and you get it, huh? So they are not moving at all. Remember, this ball came in and hit that one and it was stopped. And these guys never moved. They just instantly transferred their momentum to ball 5. It was the only one moving after the collision. Good job, David. So next, we go to Vanessa. And Vanessa, I would like you to tell me their momentum. They all have the same momentum because they all have the same mass and they all have the same velocity. So you get to calculate momentum. Vanessa, what do you got?
Would it just be 0?
It's just 0 because anything times 0 is obviously 0, right? Good job. Okay, now the part that we have to think about the hardest. Like I said, at this point, we're going to work backwards. We got to find the total momentum in order to find the velocity. We have to do total momentum first. Okay? So think about it a minute. Who am I picking on now? It looks like Kaylee. I'll give you a hint. Your total momentum after the collision is all of these added together, right? All 5 balls. And remember this. Momentum is conserved before and after the collision.
Wait, what was the one for ball 5?
That's what we have to figure out. We have to figure this one out backwards. To do that, we have to think about the fact that momentum is conserved in this collision. And that means what? Momentum is conserved. We don't gain momentum, we don't lose momentum, but we can transfer it. So ball 1 came in with some momentum, huh?
Yeah.
It transferred all that momentum through the system to ball 5. Momentum is conserved. That's your big hint.
Isn't it just 0 too?
Not quite, because remember that the momentum before will equal the momentum after, the total momentum. All right, so let's look back up here. What was the total momentum before the collision?
10.
Yeah. If momentum is conserved, and that's a law of the universe, so it is, if it's a perfect system at least. If the momentum before was 10, then the momentum after must also be
10.
10. Right? So it takes a little reasoning on that one. It's not actually doing math right here. It's thinking about this law of conservation of momentum. And like I said, when you do page 16 on your own, you're going to have to take this same approach. Okay? In order to find the velocity, that's what we're trying to do, right? What does the velocity of M5 have to be? In order to find that, we have to work backwards here. And the way you work backwards is remembering that momentum is conserved. So whatever the momentum was at the beginning, in this case it was 10, I think the one you're going to do on page 16 is more like 80,000 or some ridiculous big number. But whatever it is before the collision, it's going to be the same after the collision when you add all the individual components together. In this case, we had 5 balls to add together, right? Good job, Kaylee. So, who's next? It looks like Sam is up. So Sam, you're going to find this one out, which actually should not be too hard. This is the momentum of ball number 5. And remember, the total momentum after the collision was the momentum of all balls added together. So we haven't figured out this one yet, right? This one's got to go up there. But we already figured out these ones. Where were they? Oh, they were right here, weren't they? So Sam, what is this going to be? The momentum of ball 5 is going to be how much?
Is it going to be 10?
It's going to be 10. Perfect.
Yeah.
Why is it going to be 10? Well, because we know the total was 10. And we also know that balls 1, 2, 3, 4 weren't moving. They had no momentum. All of the momentum from the initial collision was transferred to ball number 5, right? Now imagine that in your mind. The first ball swings down, slams into the other ones. They don't move, but ball 5 swings up pretty much the same height as the first one was dropped from, right? Didn't all the momentum from ball 1 get transferred to ball 5? And as we remember back here, ball 1 had a momentum of 10 kilogram meters per second. And the same thing is true for ball 5. All of its momentum was transferred to that ball. Finally, we can work backwards using algebra to figure out the velocity. Let's see, whose turn is it? It looks like, oh, order of people got changed a little bit. Looks like it's Andres's turn. So Andres, I want you to remember, if P equals m times v, and we want to find v, don't we just divide both sides of the equation by m to get v by itself? In other words, isn't P divided by M equal to V? Right, just using algebra?
So are you saying we would divide like 5 by 10?
I'm saying, be careful, divide them in the correct order. Remember, P is on the top, so that's the
Yeah.
first number.
So 10 by 5.
10 divided by 5 equals?
2.
Yeah, simple. I wonder why that happened. Now, does this make sense? We're saying that ball 5 went swinging out at 2 meters per second, right? How fast did ball 1 come swinging in the first place? Shouldn't it be the same? Right? Came down at a speed of 2 meters per second. Ball 5 went swinging up also at 2 meters per second. Does that make sense how we did that? Because you're going to need to do this on your own in a minute on the other side. The numbers are going to be a little trickier, but the whole key is you find out the beginning momentum of a moving object colliding with a stationary object. Because momentum is conserved, you know that whatever the momentum was before is going to be the same as the momentum after. This object is going to have 0 momentum, which means all of it was transferred to the other object, and then you just have to divide to find its velocity. Okay? But before we go there, please do this momentum diagram of Newton's cradle after the collision. If I was you, I would just click. I think you have to activate your circle again. Then you can click on a circle and you can copy paste, right? Drag it down to where you need it to be. You're going to need 5 of these, correct? Let's go ahead and do that ourselves. So take a moment to draw the vector diagram. Make sure you're showing which ball is moving and which ball is not moving. Make sure you're showing the balls as the correct size in relationship to one another. Also notice that they labeled every one of the balls here. You don't have to use a subscript, you can just use M1, M2. Something like that. So go ahead and finish that vector diagram yourself. And then give me a thumbs up when you're ready to move on. Thanks, Jose. All right, Gus, good job. Yay, Vanessa. Good job, Sam. All right, David, way to go. All right, Kitsali and Kaylee, good work. Okay, so I'm hoping that in a way that your diagram, in a way, is a mirror image of this one. So you can check this for yourself. I'm not going to do it for you, but see if this makes sense. You should have, like this has one ball by itself and four together. You should have that same thing, except on the opposite side, four together on the left, one by itself. And that one by itself should have an arrow showing that it's moving. And that arrow should be equal in length to our original arrow because momentum was conserved. It has the same momentum of 10 kilogram meters per second when it came in as the 10 kg m per s as it comes out, right? Also, you should have a boundary drawn around your system. Sometimes we forget to do the boundary. Okay. Oh, one other thing it should have is the total momentum should be labeled. So don't forget to label that total momentum in your diagrams. All right. Now, page 16 is mostly going to be for you to do by yourself. It's kind of like the test. And it's the last page of the unit. How awesome is that? Number 5 should be pretty easy. It's just calculating momentum and drawing a vector diagram for it. Boom, that's all it is. No collision here. You're done with that one. But then number 6 gets to be tricky. So let's look at that together before I turn you loose. First of all, let me just point out 6A, you're finding the momentum of a train. Train number 1, which we can call T1, and it has mass 1, it has its velocity 1, it has its momentum 1. 6B, you find the momentum of another train, T2, which has its own mass, velocity, and momentum. Now, this problem is a little trickier than the one we just did with the collision of the Newton's cradle, because every ball on the Newton's cradle had the same mass, but that's not true for these two trains. So be careful on those. So this is before the collision. You find the momentum of train 1, you find the momentum of train 2, and then you draw it. When you draw the vector diagram, again, make sure you put the arrow only on the one that is having momentum. Look, this one's not moving, huh? Okay, so that one should not have an arrow on it. Also, make sure that you show me that one is bigger than the other. So when you draw your train with a box or a circle, whichever one you like, this one should be obviously bigger, right? One way to do it might be, oh, this one's 3 and this one's 2, 30 and 20. You could reduce that down to 3 and 2. You could draw one box. There's train 1, 30,000, and then there's train 2, 20,000. That would be fine. And they'd be perfectly in scale to one another too, wouldn't they? If you did that. Make sure you label them. Make sure you label the total momentum of the system at the end. Okay? Then, so this is ABC before the collision of these two trains. DEF will finish the project for you. This is now the same thing except after the collision. And there are a couple things to pay attention to. One is that when they collide, it stops the first car completely. So it is not moving now. So 6D, you're going to find the momentum of train car 1. Should be easy. After it collides, it's not moving. Also keep in mind it hasn't gained or lost any mass. But train car 2 moves forward. So down here at 6e, oh boy, you have to find the momentum. You have to find the velocity. It's not giving it to you. This is where you had to do that thing where we work backwards. Okay? And you have to keep in mind, like we did here, that momentum is conserved. So whatever the momentum was at the beginning of the total system should be the same as the total momentum at the end. Knowing that momentum is conserved, it's going to allow you to work backwards on this. You'll know the mass, you won't know the velocity. But you will know the momentum because momentum was conserved. That will allow you to find the velocity by working backwards. So this is what we're going to do. I am going to say farewell, auf Wiedersehen, have a great holiday, all those things. And I'm going to leave the meeting running on my computer in the background. And so if you get stuck on any of this, or if you need help on any of the older pages, you are welcome to, just come back to the meeting and ask for help. So you can leave the meeting. This is due at the end of the day. Okay, you should finish this whole project today. We have about an hour for you to work on it. I'm going to leave the meeting running. If you need help, ask for help, okay? So if you have any questions about this or any other assignments or anything, stick around. If you need help on any of this stuff, please let me know, okay? Because I'll be here. And I hope you have a great holiday, a safe holiday. Have fun, rest a little bit. Maybe spend some time making up some missing work if you have any to do, though, because the semester is going to fly when we get back, right? All right, that's all I have for you guys. Have a good one.
Thanks, Fairly. Happy
Thank you,
holidays.
Fairly.
Bye.
Bye. Thank you.
Adios. Thanks, guys.